So the videos of the first three lectures are on YouTube. You can look at them if you missed class, or if you want to figure out what it was that I actually said in class, then you can look at the video. We were talking about Lagrange multipliers last time, and the basic idea is that you have some function f of various variables x1 to xn, and you want to find where it has maxima or minima, or just extremal points, stationary points, but subject to various constraints, c1, c2, x3 dot 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 equals, well, the constraint is that that is equal to 0. And so what you do is you define a new function, which is a function now of all the x's and lambda, and this is f of x. I often, and let's be clear about this, maybe I haven't been clear enough about it, but I often jump to matrix notation where just an x is a vector and another letter stands for a whole matrix. So this is then mine, and there might be several constraints. So CK, say, and this would then be minus lambda k ck of x. So we define something like this. This is a function of, let us say there are L constraints and n variables. This is a function of n plus L variables. And you find the minima of this function by differentiating with respect to all n plus L variables. And the idea is that that basically the gradient of f can be a sum of the gradients of the various constraints. So that's the picture. Let me give you an example. There's an example in the book for a case where A is a real symmetric matrix. I thought what I would do was give you another example where where A is a Hermitian matrix. In fact, I don't even think it needs to be Hermitian. In this case, suppose we're looking for stationary points of W bar AZ, and we're subject to constraints. Z bar Z is 1, W bar W is 1. Once again, I'm using a vector notation here. And so you define L equal to W bar AZ minus, let us say, lambda 1, Z minus W, and lambda 2, W bar W minus 1. So this says that W is a unit vector, and this says the vector Z is W. So we're looking for stationary points of this thing where W and Z are the same and both are normalized. And so, and again, this is vector notation. notation, and sometimes I indicate vector notation like this. And if the indexes are repeated, we sum over them. So in general, in this course, in the book, and so forth, an index is repeated, we sum over it. Okay, so what do? We apply this rule, we take partial L, partial W bar I, say. Well, that is AIK, ZK. And this is W bar, so we get minus lambda 2 WK. And then we differentiate with respect to ZK, and we get W bar I AIK minus lambda 1 let's see here. I didn't expect that this would turn out that way. I think I actually made a mistake in. All right, let me follow this through and see what actually happens. This strikes me as a little bit bizarre now. Wait, we would, yeah, all right. So this constraint now says W is equal to Z. And if W is equal to Z, then what we have is that AIK ZK is equal to lambda 2 ZK. So that's what I was looking for, namely the eigenvalue equation. Yeah, let's forget about differentiating with respect to. Another way of thinking about this, by the way, a much simpler way, is to imagine that we have Z bar AZ. And so we define L equal to this minus lambda Z bar Z minus 1. So this is just having one complex vector A in a matrix, a complex vector Z in a matrix A. Then you say partial L, partial Z bar. This gives you A, IK, say, ZK minus lambda ZK. And so that's the eigenvalue equation immediately. And you don't have to fuss with anything else. So that just says AZ is equal to lambda Z. So lambda is the eigenvalue. So what we learned from this is that if we focus on inner products like this or like that, and requires, let's just focus on this kind, Z bar AZ. The stationary points of this are where Z is an eigenvector of the operator A, or the matrix A. And in this, I didn't even use hermiticity or anything. It's just that any matrix there will be, any matrix in a product will be stationary with respect to the variations of the vectors if the vector is an eigenvector, assuming that we fix the normalization of the eigenvector. And in quantum mechanics, that corresponds to the statement that we normalize the wave function integrating over space. It doesn't matter, it's not necessary that we normalize it to unity, we just have to normalize it to something. And then one has that result. You might worry a little bit that here I'm regarding Z and Z bar as independent variables. One can do that in the sense that Z is a linear combination of two independent variables, X and Y. And if you differentiate with respect to X and Y, those are linear combinations of derivatives with respect to Z and Z. All right. Any questions? All right, let me go to the next topic here. Eigenvectors and eigenvalues. So this Lagrange multiplier thing has led us naturally to consider eigenvectors and eigenvalues. And if we have a matrix A, a vector U, a number lambda, and the same vector U, we say that this is an eigenvector. And that this is an eigenvalue. And eigen is a German adjective that means own, special, or proper. So this is somehow the proper number of this operator, the special number of that operator. Now, if we have vectors k from 1 to n, say n vectors k, that form an orthonormal basis on this vector space, then of course we can write the identity operator as a sum of the outer products of the k's, and then, or equivalently as a sum of outer products with different index L, and if A is n by n, then there'd be n of these. And then we can take the matrix element of this, KAIU, well this is KA, and we substitute this expression, we have LU, and so this is then a sum, L equals 1 to n, and so this is also, since I just stuck in the identity operator, this is the same thing as KAU, and so this says that, and another way of, well, this says that KA acting on U, A can be represented by this matrix. And so the kth matrix element of a vector AU is a sum on L of AKL U sub L, where U sub L is LU. Yeah.
What is the identity operator, and what is it doing here?
Okay, hold on, let me throw you this candy. Oh, almost. So, I just stuck the identity operator in here. I wanted to say I wanted to show that KAU was equal to this sum. And one can always stick the identity operator essentially anywhere because it doesn't change anything. And the identity operator is always a sum of outer products of orthonormal states, a complete set of orthonormal states.
And that sum of outer products just yields a one. That sum of outer products is just a matrix with ones on the.
Well, it is the identity operator, depending on, you see, a matrix depends upon the representation. So if you take the matrix, if you take this matrix element and look at A sub I, the identity A sub j, well, this will be a sum on K of AI, let us say K, AJ. And if you, so in the A basis, it is whatever that happens to be. Now, alternatively, if you take the k's and write them as some basis. You might write 1 as some vector, say 1, 0, and you might say 2 is 0, 1. Then what you would have is that 1, 1 plus 2, 2 would be 1, 0, 1, 0 plus 0, 1, 0, 1. And so this would turn out to be 1, 0, 0, 0 plus 0, 0, 0, 1. And so when you add those together, you get what you were talking about, namely a diagonal matrix with. But this vector 1 we represent this vector by this particular column vector only in a particular basis. Okay. Now, one interesting aspect of eigenvectors and eigenvalues is, suppose CL, UL plus up to, let us say, CR, UR is a subspace. This would be a subspace spanned by these vectors. That subspace is left invariant. So in other words, by the action of A. So A on this, if these are all different these are all eigenvectors of A, this will be this would be a sum on L of CL A U sub L plus dot 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 plus CR A UR, and, well, I don't need that parenthesis. And this would then be a sum CL AL UL plus dot 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 plus CR AR UR. So this again is a vector in the space that's spanned by the eigenvectors of the matrix. So you can take any collection of eigenvectors of a matrix and you consider the space spanned by that set of eigenvectors. That space remains invariant when you act on it with A. A maps any vector, any linear combination of its eigenvectors into another linear combination of its eigenvectors. So I think actually that's more obvious than all the words I used to explain it. Okay. The next is really something important, the eigenvectors of a square matrix. So let's once again have A be an n by n matrix. So A is an n by n matrix, and V is an eigenvector. So what we have then is AIK, VK, sum k equals 1 to n is some eigenvalue times VI. Or in matrix notation, it is AB is lambda V. All right, now you can visualize this matrix as a bunch of columns, which of course it is. And you can see here that the kth column gets multiplied by VK. So this equation says that V1 times the first column of A plus V2 times the second column of A up to Vn times the nth column of A is lambda times the vector V itself. So that is saying that the set of vectors, that these vectors are linearly dependent. That is to say, the vectors of the matrix A minus lambda I, the columns of this matrix are linearly dependent because these columns would be, if these columns, if you do it this way, A ik minus lambda delta ik vk equals 0. So that's what the eigenvalue equation says. So if you imagine the columns of this matrix, this statement says the columns of this matrix are linearly dependent as long as some of the vk's are non-zero. And something about an eigenvector is we exclude always the trivial case of the zero eigenvector, because the zero vector is an eigenvector of every operator with eigenvalue 0. So we forget about that one. So this is saying that the columns of this matrix are linearly dependent. So that means that the determinant of this matrix, A minus lambda I, must vanish. And one often writes determinants as just two straight lines, so you don't have to write DET. Now this determinant is a polynomial in lambda, and it's called the characteristic polynomial. So this is P of lambda and A. So this is called the characteristic polynomial. And it has to vanish. So it's a polynomial in lambda, and it's equal to 0 whenever lambda is an eigenvalue. Now, this is a polynomial of nth degree because the highest terms in this polynomial will be, this will be a sum. In fact, let me write the thing out more simply. P of lambda A, if you imagine expanding this thing, the term with lambda, that's the 0th power of lambda, is just determinant of A. So the first term is determinant of A. Then there are various terms that are harder to describe until one gets to the n minus first term, and that's lambda to the n minus 1. And that's the trace of the matrix A. And then the last term is minus 1 to the n, lambda to the n, and that's for the case where, that's the term that arises from the term in the determinant in which you just take, you multiply minus lambda times itself along the main diagonal here, n times. So that's minus 1 to the n, minus lambda to the n. So that's what that is, and that's a polynomial of nth degree in lambda. And there's a theorem which we'll prove in a couple of weeks, or maybe 3 or 4 weeks. That's the, I guess it's the fundamental theorem of algebra, and it's actually a theorem of complex variable theory. And it's that any function, any polynomial of nth degree has n complex roots. So there are n lambdas somewhere in the complex plane such that that vanishes. And what we'll learn a little bit later today is that if the matrix A is Hermitian, then the eigen values are actually real. So this is very, very special. It means that for a Hermitian matrix, the eigenvalues don't lie just somewhere in the complex plane. They all lie on the real axis, which is an enormous compression of the whole plane into the real axis. Okay, now, I'm going to write P of lambda A as a sum, k equals 0 to n, lambda to the k, pk, p sub k. And one interesting thing is that the pk's are basis independent. And the reason for that is that these are coming from this determinant. And so if we took P of lambda A prime, by which I mean P of lambda S A S inverse, so we make this is called a similarity transformation. A similarity transformation, this is the same, and what we'll see is that the p's are the same. And the reason is that this is the determinant of SA S inverse minus lambda I. But this is the same thing as S A minus lambda I S inverse, the determinant of that. And we learned about determinants, that the determinant of the product is the product of the determinants. And we also learned that the determinant of an inverse is the inverse of the determinant. And so this is actually the determinant of A minus lambda I, which actually is P of lambda A. So what we see is that if you make a similarity transformation on the matrix, the characteristic polynomial doesn't change at all. And that means then that the pK's are independent of basis. We can gather together all of the eigenvectors of the matrix A. We see that we have n of them. We have n of them because there are n roots to this characteristic equation. So what this tells us then is that a square matrix always has n eigenvalues and n eigenvectors. What is not necessarily true, and what it doesn't tell us, is that these eigenvectors are linearly independent. Sometimes they're not linearly independent. But you don't have to worry about that case much, because in that case we call the matrix defective. And then you can just say, I'm not bothered with that, it's defective. Okay. So any matrix that's not defective has n orthonormal eigenvectors that form a basis. By the way, since these eigenvalues are the roots of this polynomial, we can rewrite this as lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n. So the characteristic polynomial can also be written just as in factorized form as a product of terms lambda minus a particular eigenvalue. Now, if we gather together for any square matrix its n eigenvectors, we can form them into a matrix V whose elements are, it's the ith component of the kth eigenvector. And then we can look at the product, AV. And AV, for example, has element is a matrix in which the element of the ith row and the nth column is the sum, k equals 1 to n, of aik v, well, it's actually vk l, or equivalently a sum, aik vk l. So now this is the nth eigen, the kth element of the nth eigenvector. This thing is called the modal matrix. And if you do this multiplication, you see that for a given L, this product here is a sum, we're summing on K, it would then be lambda K VK L. And another way of thinking about that is that it is a sum on K of V. Let's see, I've done, yeah, I was a little sloppy here. It's A acting on this, so it is lambda K, but it's I K, because, let's see, do I have it right? No, it's IL. No, it's lambda L. I should read my notes. Anyway, we can rewrite this as VIK delta KL lambda L. And now we can rewrite that as the sum on K of VIK, the diagonal form of A. And it's the KL diagonal form. So AKL diagonal is equal to lambda L delta KL. Well, delta KL because it's diagonal, but of lambda. So what that tells you then is that AV is V A diagonal. So you form a modal matrix out of the eigenvectors of a matrix. You do that multiplication, you get the modal matrix back, and then you get a diagonal matrix of eigenvalues. Now, as I said, most of the time, generically, the eigenvectors of a square matrix are linearly independent, and consequently, the matrix whose columns are the eigenvectors, since they're linearly independent in general, that matrix will be non-singular, and so it will have an inverse. And in that case, what you can do is you can write V inverse AV is equal to AD. So that says that a non-defective square matrix can be diagonalized. Remember, if it's non-defective, the eigenvectors are linearly independent. What we saw over here was that if you set lambda equal to 0, P of 0A is just the determinant of A. So, and that's the product of all the eigenvalues. So, let's see, one thing that I sort of assumed in the last few minutes without actually proving, and now I'll show you why it's true. It's that if the n roots, as I said, a polynomial of nth degree has n roots, n eigenvalues, n roots in the complex plane. And usually the roots are different. And when they are, the eigenvectors are linearly independent. What I want to show you is, I want to show you now that that's true. That is to say, if the roots are different, then the eigenvectors are linearly independent. Well, the first eigenvector obviously is linearly independent because any single eigenvector is linearly independent. So let's assume that for some k less than n, these guys are linearly independent. So the first k eigenvectors are linearly independent. So I want to show that the first k plus 1 eigenvectors are linearly independent. So we assume the contrary. And the contrary is that the sum L equal to k plus 1 CL VL is equal to 0. That is to say, if we choose the first k plus 1 eigenvectors, we can find coefficients that are not all 0 such that the sum is 0. These will be linearly dependent. Okay. So what we do is we use the fact that these are eigenvectors. So we multiply by A. So A sum CL VL is then a sum CL A sub L VL up to k plus 1. And then we take this same sum and we multiply by the sorry, this is supposed to be lambda. This is the Lth eigenvector. So A on VL is lambda L VL. So now we multiply by lambda k plus 1, and we get, and we're assuming that's 0, so we get a sum CL lambda k plus 1 VL. And we have that this is 0. So we're assuming that that's 0, and we get two 0 equations then from it. One of them is by multiplying 0 by A, and the other one is multiplying 0 by lambda k plus 1. Now we subtract, and you see the last term cancels. And so what we get when we subtract is just a sum L equals 1 to k, CL lambda L VL equals 0. But the that means that these guys are linearly dependent. No, I went too fast. I really should follow the text more carefully. What we do now is we subtract. We subtract this from this, and then we get the statement that 0 is a sum. Yeah, that's right. Sum CL lambda L minus lambda k plus 1 VL. So that's what we get equal to 0. In other words, we've subtracted this from this equation, and we just get lambda L minus lambda k plus 1. But now what we've assumed is that the eigenvalues are all different. If the eigenvalues are different, then these are non-zero. And consequently, since the C's are not all zero, this cell says that the sum up just to L, because the L, K plus, up to K is, in other words, we're getting the sum up to K, CL, of lambda L minus lambda K plus 1, VL, vanishes, where these guys are all different because we assume the eigenvalues are different. All right, so the upshot then is that all n by n eigenvectors of an n by n square matrix, if they have different eigenvalues, then they're linearly dependent. And typically, there's only one eigenvector associated with each eigenvalue. In that case, it's said to be a simple eigenvalue. So if lambda has one v lambda, then lambda is a simple eigenvalue. On the other hand, sometimes an eigenvalue will have an eigenvalue will occur. In other words, the characteristic equation will have more than one root. Will have one root that is that occurs more than once. So, in other words, in this factorization of p of lambda and a, one might have a term that is lambda minus lambda star cubed, and then various other terms. So this would be lambda star would have multiplicity 3. And so then it's said to be threefold degenerate, or to have algebraic multiplicity 3. Now, so this eigenvalue has algebraic multiplicity 3. The question then is, what is its geometric multiplicity? The geometric multiplicity of lambda star is the number of eigenvectors. If it has 3, then that's great, because there are 3 different or linearly independent eigenvectors with this eigenvalue. Then the geometric multiplicity and the algebraic multiplicity are the same. Anyway, to get to the bottom line, it's if an n by n matrix has n linearly independent eigenvectors, then it's non-defective. Then A is non-defective. If, on the other hand, A has fewer linearly independent eigenvectors, then and it's n by n, then it's a defective matrix. And every non-defective square matrix can be diagonalized by its modal matrix. So you have B inverse AB is the diagonal form for all non-defective square A's. Let me just mention that we've seen that the determinant of A is the product of the eigenvalues, and the trace of A is the sum of the eigenvalues. And so then you can see that the determinant of A can be thought of as e to the sum of the lambda of the log, sum of the logs. But that is e to the, let's see, how do I want to say it? E to the trace of the logarithm of the matrix. And so you can say determinant of A is the determinant of e to the log of A, or it's exp of the trace of the log of A. An example of a defective matrix is 0, 0, 1, 0. That's a 2 by 2 defective matrix. Okay, the next topic is that every matrix obeys its characteristic equation. This is quite remarkable. I found it useful because if the matrix is small, 2 by 2, 3 by 3, I guess mathematicians use it more broadly in the case where, in the general case, certainly it might be useful in a computer program approach. In other words, the use of computers can handle large matrices, and the fact that every matrix satisfies its characteristic equation may make it possible to write nifty programs for linear algebra. In fact, marvelous programs already exist for linear algebra. You can do almost anything, and you can download these programs for free if you want to get them from the web, various places. All right, so as I said, what I want to show now is that P of lambda A, which of course is A minus lambda I, and this is a sum, K equals 1 to N, PK lambda K equals 0. So that's the characteristic equation. What I want to show now is that P of A comma A, which is the sum K equals 1 to N, piece of K, A to the K is 0. So this is quite remarkable that the matrix itself, the whole n by n matrix, satisfies its characteristic equation. And of course there are n terms here. So if suppose A were 1,000 by 1,000, then there would be, actually this is a sum from 0. Then there would be 1,000 plus and 1 terms in this expression. And each term would be a product of 1,000 by 1,000 matrices. So from the human perspective, this is impossible. From the computer perspective, it's Dr. Soup. I don't know what Dr. Soup had indicated. That's what people say. All right, let us use our formula that we learned, in fact, only a couple of days ago. Well, no, you guys probably learned it years ago. That the inverse of a matrix is the transpose of the cofactor matrix divided by the determinant. So this thing here is the transpose of the matrix of cofactors of A minus lambda I. So there's A minus lambda I, you take the cofactors, that forms a matrix, and you take the transpose of that matrix. So that's our formula for A inverse. And so what we can find is then, a little algebra tells us that A minus lambda I times the cofactor matrix transpose is equal to the determinant of A minus lambda I. And this, of course, is, well, if you want, times the identity. And this is equal to the characteristic polynomial times the identity matrix. So this is a matrix equation. Now, what we're going to see is a gigantic cancellation. First of all, we're going to write this transpose cofactor matrix as C0 plus C1 lambda plus, let's say, C2 lambda squared plus dot 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 plus Cn minus 1 lambda n minus 1. So these are cofactors of this. So this matrix is only a polynomial of degree n minus 1. Because when you make a cofactor, you strike out a column and a row. So that's what C transpose is. And now what we're going to do is we're going to multiply that by this. And if we do that, we get A minus lambda I, C of lambda and A transpose. This is A C0 plus A C1 minus C0 lambda plus AC2 minus C1 lambda squared plus dot 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 plus ACN minus 1 minus CN minus 2 lambda n minus 1 minus Cn minus 1 lambda to the n. And this is then C is pk, lambda is the k equals 0 up to n. So what we've done here is just written this we've written this as a polynomial in lambda, and we've used the fact that that the characteristic polynomial itself has this expansion in terms of the pk's and the lambdas. So we have this then expression here, because this whole thing by this equation is the determinant of A minus lambda I times the identity. All right, so that's our expression here. Now what we do is we equate. This is an equation then, and I'm looking at this part of the equation. This complicated thing equals this relatively simple thing. Both are polynomials of degree n in lambda, and lambda is a variable. In fact, in general, it's a complex variable. And so we can, if we have an equation for arbitrary lambda, that's a polynomial equation on both sides, we can equate, if this is an equation of degree n, and the powers of lambda go from 0 to n, so this gives us n plus 1 equations. And the n plus 1 equations, by equating equal powers of lambda, are AC0 is P0I, AC1 minus C0 is P1I, AC2 minus C1 is P2I, down to AC Cn minus 1 minus Cn minus 2 is Pn minus 1i minus Cn minus 1 is Pni. Okay. Now, we still don't have the cancellation, but now the magical gigantic magical cancellations are going to occur. What we do is we multiply from the left the first equation by I, the second one by A, the third one by A squared, and the last one by A to the n. Okay, so if we multiply the top equation by I, and this one by A, we see that AC0 will be canceled, and then we add them all together. The AC0 will be canceled by minus AC0. Then down here, AC1 will be canceled by minus AC1. ACN minus 1 will be canceled by minus ACN minus 1. So on the left-hand side, we get 0. And we add everything. On the right-hand side, what do we have? We have P0 just times the identity. We have P1 identity times A, P2 identity A squared plus dot 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 down to this one we multiply by after all, we multiply this by 1, this by A, this by A squared. So it's A squared cancel A squared. So the last one here is minus A to the last is by AN C n minus 1. No, I'm sorry, it's not that. It's Pn. Sorry, I screwed this up. The last one, let's see, this is I, this is A to the n, so this is plus Pn I A to the n. So, but this, if you forget about the i's because they're just identity matrices, this is just the statement that P of AA equals 0. So, every square matrix satisfies its own characteristic equation. This is something that is called the Cahill-Hamilton theorem. The proof that I put in the book is one I got from a Russian mathematician named Gelfand, who is remarkable not only in being a remarkably distinguished mathematician, but he actually writes very clearly. So if you want to learn something in deep mathematics, Google Gelfand and then whatever it is that you want to find out in deep mathematics. And if he has explained it, read his treatment. The man's name is Gelfand. He left the Soviet Union, I don't know, sometime like 30 years ago or something, 40 years ago. Died maybe 10 years ago. I think he was teaching at some university in New Jersey. Anyway, wrote marvelous books and articles. So let's see, how's the time doing? Well, we've got a little bit of time. So every matrix obeys its characteristic equation, and in particular then, you can take the nth power of any matrix and you can write it as minus 1 to the n minus 1 times A times the identity plus P1 times A plus dot 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 plus minus 1 to the n minus 1 trace of A times A to the n minus 1. So this is expressing, if you have an n by n matrix, you can express the nth power of that matrix in terms of the lower powers. So then if you want to compute an arbitrary function of a square matrix that's n by n, you only need to compute the matrices that are the first n minus 1 powers of the matrix. And you put them together and you're good to go. I give an example of that that's useful, namely manipulation of the Pauli matrices. In fact, there's a remarkable little identity that you can prove using this formalism, e to the minus I theta dot sigma over 2 is cosine of theta over 2, theta being the length of theta, times the identity minus I theta hat dot sigma sine theta over 2. So that's very useful in quantum mechanics when you talk about spin 1/2 systems. And in one of the exercises, actually, you're supposed to derive that thing. And that's an exercise that's certainly worth doing. And you can use this Cahill-Hamilton theorem to derive that. I actually used it to do the 3 by 3 case, and that was about the limit that my fingers could get to. When it comes to 4 by 4 matrices, I give up and go to the computer. Okay, functions of matrices. Well, suppose you have some function f of x, which is, say, some infinite series ck x to the k, and suppose it's well behaved, it converges, so on and so forth. And what you want to do is you want to say, well, what is f of a? Well, what you can always do is you can write it as a sum k equals 0 to n minus 1 f sub k of p. P is an n minus 1 dimensional vector, a to the k, where these things are coefficients that depend upon the coefficients of the characteristic polynomial for the n by n matrix A. So in other words, you can write f of A as a polynomial, even though it's an infinite series, you can write it as a series of n terms with certain coefficients. And the coefficients depend upon the coefficients in the characteristic polynomial. And I give an example there, which, as I said, was the limit of my ability to compute things with my fingers. However, there's something more abstract that's, I think, much more useful. Namely, suppose A is non-defective. If it's non-defective, then we can write A as S, a diagonal matrix, S inverse. And then F of A diagonal, well, this will obviously be a sum ck A diagonal raised to the kth power, and all this will be f of A1 0 0 0, f of A2 0, and so on and so forth, down to f of An. And another way of thinking about that is to say, well, this what is f? So that's what f of AD is. Now f of A is the sum ck ak, but this is the sum ck s a diagonal s inverse to the kth power. On the other hand, what happens is, here, let me just show you that for the, so, let's just look at the second power. C2 S ADS inverse S AD S inverse. Well, you see this collapses into the identity matrix. So what you get is S AD squared S inverse. And so this thing here is nothing more than S, a sum CK AD to the K S inverse. This is AD here. Well, no, that's A. What am I doing? That's AD to the K. So this is right. What I have here is AD to the K S inverse. This thing is that. So this is a diagonal matrix, and so we can write the function of any non-defective n by n matrix as the n by n matrix that diagonalizes it, the inverse of that matrix, times the sum, the infinite sum, ck ad to the k, and that just gives you an n by n. So in other words, it's S, and this matrix f of a1 down to f of an, S inverse. And in fact, what I should have said was, this is the nodal, this is the modal matrix, which I called V, so I could have called this V inverse, which was maybe. But I'll just write there. Okay. So now there are various examples that I'll do, if you want me to, I'll do them in the problem session next week, but we don't have time for them. Anybody going into quantum information theory should learn about Glauber's identity. And there's something about chemical reactions, something about the time evolution operator, something about entropy that's quite important. So I'm going to do some of these examples in the problem session. By the way, there is I did make a website called, it's just my name, middle initial, and last name. You go to GitHub or GitHub and / my name, middle initial, last name, and you can find all sorts of programs, MATLAB programs, Fortran programs, mathematical programs that I use to do various things, figures, or to, in fact, to compute these curves and so forth. But we don't have that time in class. Okay, Hermitian matrices. Let's see if we can finish this in. So this is a special case of the non-defective matrices. So let's say we have an n by n matrix A. We know it has n eigenvectors and eigenvalues. Let us now assume that the thing is Hermitian. So we use Dirac's notation to rewrite this as AK complex conjugate, bra K, and then we use the fact that this is that the matrix is Hermitian to write this as Ka equals AK star K K, and now we form the inner product of these two equations, and what we get is K, the diagonal matrix element of A is here. It's AK star KK, and let's assume that we've normalized to unity all these eigenvectors of the square matrix A. and taking the matrix element from the left using the bra k, what we get is AK, KK. Remember that eigenvectors are always non-zero vectors, so we can divide by that, and we get that AK star equals AK. So, the eigenvalues of a Hermitian matrix are all real. Now, let's get to the next point. The next point is to consider the complex conjugate of a particular eigenvector times this inner product, mk. Now, using Dirac's notation, this is km complex conjugate, and that's the same thing as KAM complex conjugate, because A on AM is A sub M. And this is the same thing as M A dagger K. Again, I'm leaning on Dirac. On the other hand, the thing is Hermitian, so this is M A K. And K is an eigenvector of A with eigenvalue AK. So, putting all this together, we have AM star minus AK times MK equals 0. So what does this tell us? This tells us that, well, first of all, we already know that the eigenvalues are real. So we erase the complex conjugation. We have this statement. What does this say? This says that if the eigenvalues are different, the eigenvectors are orthogonal. That's a nice property of Hermitian matrices. So, on the other hand, sometimes the eigenvalues can be the same for a Hermitian operator. And in this case, we say the eigenvalues are degenerate. And in this case, for example, A times a sum arbitrary coefficients of these degenerate eigenvectors gives us the same eigenvalue times C alpha K alpha. So any linear combination of these degenerate eigenvectors is an eigenvector with the same eigenvalue. Clearly. On the other hand, what we can do is we can take these, if these, to the extent that these eigenvectors are linearly independent, we can make them orthonormal with Gram-Schmidt, as long as they're linearly independent. But then two questions arise, which I guess we'll discuss next time. The first question is, are the degenerate eigenvectors linearly independent, or when are they linearly independent? And secondly, if we do have, if they are linearly independent, what linear combinations of the degenerate eigenvalues should we take? Should we use in any particular physics problem? So I'll address those questions next time. We're basically out of time now.